Okay, let's talk about something that sounds like it's straight out of science fiction, but it's really not. What if the very steel and concrete that hold up our world could actually think? Today, we're diving into this amazing new world where artificial intelligence meets heavy-duty engineering. We're asking, can we actually give our infrastructure a mind of its own?
I mean, just imagine it for a second. A bridge that doesn't just sit there, passively taking a beating from traffic and weather. Instead, it's alive. It's actively monitoring its own health, feeling out its own weaknesses. And crucially, it warns us before something catastrophic happens. This isn't just some daydream. It's the very real goal engineers are chasing right now.
So, here's our game plan. First, we'll get into the core idea of what a smart structure even is. Then, we're going to tackle the 3 huge hurdles that engineers are facing. And finally, we'll get to the fun part, looking at the incredible future that's waiting for us once we clear those hurdles.
All right, let's dive right in. The quest for smart structures. What are we really trying to do here? Well, it all boils down to one absolutely fundamental principle in engineering.
And that principle is summed up in one word: stiffness. You can think of it as a material's stubbornness, its refusal to change shape. When you push on it or pull on it, how much does it fight back against bending or deforming? This one single property, it's the bedrock of safety and reliability in literally everything, from the tallest skyscraper to the airplane you fly on.
So the big dream here, the ultimate goal, isn't just to get better at measuring stiffness. It's to use AI to predict it, to manage it, and maybe even to actively control it. This would let us create structures that can literally adapt to their surroundings in the blink of an eye. But, as you can probably guess, turning that vision into a reality, well, that's a massive challenge.
Which brings us smack into our first major roadblock. I call it the data drought. Because if there's one thing we know about AI, it's that it is incredibly hungry for data. You see, training an AI for engineering is a whole different ballgame from, say, teaching it to recognize cat photos. Getting good, clean data is a monumental task. The sensors you need, like digital image correlation that uses cameras to watch for tiny deformations, are super expensive. Plus, the real world is messy. It's full of what engineers call environmental noise, stuff like random vibrations or temperature swings that messes up your data. And a lot of the time, you just don't have enough data points to train a solid model, especially for those rare but super critical events like an actual structural failure.
And hey, don't just take my word for it. This isn't some small annoyance. It's a fundamental challenge that everyone in the field is wrestling with. This quote just nails it. Unlike the online world where data is basically free and endless, in the physical world, every single data point is earned the hard way.
Okay, so let's say you somehow manage to get your hands on enough data. You immediately run headfirst into the second major challenge. And this one is almost like a culture clash, a conflict between 2 totally different ways of seeing the world. See, on one side you have your traditional physical models, things like the finite element method. These are built on the absolute bedrock of physics. We know exactly why they work. They're totally transparent. You can explain every step. But on the other side, you've got AI. It's an absolute genius at finding these incredibly complex hidden patterns in data. But it often works like a black box. We can see that it gets the right answer, but we don't always know how or why. So if you're an engineer, what do you trust? The model you can explain, but that has to make simplifications, or the super powerful one that you can't fully explain?
Well, the truly brilliant solution, it turns out, is to not choose at all. Instead, you make them partners. You build a hybrid system that gets the absolute best of both worlds.
And here's how this hybrid model actually works. It's a really slick 4-step process. First, your trusty old physics model makes a good first guess, an initial prediction. Second, you have real sensors on the actual structure, giving you the real-world ground truth data. Now third, and this is the absolute genius of it, the AI doesn't try to learn everything from the ground up. Nope, it just learns one simple thing, the error, the difference between what the physics model predicted and what actually happened. And finally, it uses that knowledge to correct the physics model on the fly, in real time, giving you this incredible, hyper-accurate result.
So, we've got a model that's both smart and trustworthy. Problem solved, right? Well, not quite. There is one final, absolutely critical challenge: the race against the clock.
For a bridge to warn you about an imminent failure, or for a car's suspension to instantly react to a giant pothole, you can't wait. There's just no time to send data off to a server in the cloud and wait for a response. The thinking, the analysis, it all has to happen right there, on the spot, in milliseconds.
And this is where the really tough technical barriers pop up. You've got latency, that's the tiny delay as signals just travel from one place to another. You have to deal with the limited computing power of the small edge devices that would actually live inside a structure, and on top of all that, the model has to keep working perfectly even as the real-world conditions around it are changing every single second. But, and this is the really exciting part, if we can successfully figure out how to navigate these three huge challenges, the data drought, the physics-AI divide, and the need for speed, we unlock a future for engineering that is truly revolutionary.
So let's just recap really quickly. These are the three big dragons that researchers are focused on slaying right now: getting the right data, making physics and AI play nice together, and getting everything to work fast enough for the real world.
In solving these problems, it's so much more than just a cool academic exercise. We are talking about a fundamental shift, a move away from building passive things that just stand there to creating intelligent, adaptive systems that can actively manage their own health and their own performance.
So what does that future actually look like? It looks like bridges that can literally call for their own repairs. It looks like airplanes built from materials that are lighter and more efficient, because we can trust their integrity with perfect accuracy. It looks like buildings that can intelligently stiffen themselves to withstand an earthquake. This is the incredible promise of what happens when we make our structures truly smart.
And this brings us to one last, really important thought to leave you with. As we start handing over more and more of this monitoring and control to these AI-driven systems, a whole new set of responsibilities falls on our shoulders. The challenge isn't just about what the technology can do anymore. It's about our duty to understand it, to trust it, and to ensure that it is, without a doubt, safe and reliable. Thanks for joining me.